In this video, we're going to talk about the definitions of acids and bases. According to the Arrhenius definition, an acid produces H+ ions in water. When we think of an acid dissolving in water, we should be thinking that its ions would be separating. So classically, we would think of H+ aqueous and A- anion aqueous. However, in reality, acids are dissociating in water. This H+ ion is actually very unstable, and it would immediately react with the water. So what the reaction actually looks like is we have H3O plus aqueous plus A- aqueous. And so what you actually have happening is you have H plus reacting with H2O to make H3O plus, which is our hydronium ion. And actually that's what's depicted right over here. A base is a compound that produces hydroxide ions in water. If we had MOH dissociate, we would have M plus being our metal ion plus OH minus aqueous. A real life example of this is sodium hydroxide. We would have Na plus aqueous plus OH minus aqueous. And remember that OH minus is our hydroxide ion. All right, so Arrhenius is not our only definition of an acid base. It's actually a pretty simple one, but is pretty narrow in its definition. The next definition we're going to talk about is the Bronsted-Lowry definitions. In this model, an acid donates a proton and a base accepts a proton. And you'll see that this definition is already more broad because previously a base was limited to producing hydroxide ions. You may wonder how these definitions would be put into action. If we look at the equation above right here, what you'll see is you have our normal acid, right? You have the HCl giving an H plus to the H2O to make this H3O plus. And so because the H plus is being accepted by the H2O, H2O is our base. So in our forward reaction, our acid is HCl and our base is H2O. However, you can also look at this reaction going in reverse. And what you'll see here is you actually have H plus combining with Cl minus to make HCl. And so in this case, H3O plus is also an acid. So we call this our conjugate acid. And so then not surprisingly, you'll find that Cl minus would be our conjugate base because it was the one who received the H plus. That means in our reverse reaction, we actually have another acid, which was H3O plus. And in our reverse reaction, we also have another base, which is Cl minus. So what you see in this picture up here is you'll actually see the movement of the H from the HCl onto the H3O plus. So just to be thorough, we'll label them again. HCl is the acid which donates the H to the water, our base. And then in the opposite reaction, if we looked at the reverse, you'll see that this H travels from the hydronium ion to the chlorine, making H3O plus our conjugate acid, abbreviated here as CONJ, and our conjugate base, the receptor. What you see is when you have a reaction going in the forward or the reverse, is that they come in pairs. So HCl and Cl minus would be a conjugate acid-base pair. We have our acid with its conjugate base, which would act as a base in the reverse reaction. The second conjugate acid-base pair would be H2O and H3O plus. You should note that these acid-base pairs always look alike. The HCl looks like the Cl minus because the only thing that's different between them is an H plus. Below is an understanding check. First, you need to determine whether or not they are conjugate acid-base pairs. If they are, then you need to write the reaction with water. And if not, you need to supply what they actually are. So write a reaction with water. So the easy thing to do is to take the acid and just react it with water and see what happens. I would write HF aqueous plus H2O. So HF is going to be an acid. If this donates to H2O, we'll get H3O plus F minus. So that means, yes, our acid base pair is correct. And you can double check this because HF and F minus do only differ by an H plus. So now I want you guys to take a moment to pause. I want you to try these next 3 problems, starting with reacting these 3 with water and then telling me whether or not you think they're a pair. Great, welcome back. So right now, I want you to check out these answers. If you got these answers correct, I still want you to check your work, but if you did not get these answers, I want you to go back, double check your work, look at the example, and try to see if you can get the correct answer before I show you all the work. All right, so here are the answers. In the first one, you can first check by seeing that if you subtracted an H and you subtracted a plus sign, you would get NH3. So that's one hint that you're in the right track. And what you'll see is when you react to NH4 with water, you do get, in fact, NH3 as its conjugate base. For C, we have H2SO4 reacting with water. It only loses one H plus at a time. So SO4 2 minus is not its conjugate base, but HSO4 minus would be. Remember that each of them need to differ by only one H plus. For D, you'll see that they're completely unrelated, and they definitely do not differ by one H plus. Question number 2. Write the conjugate base for perchloric acid. Show the reaction. So you can either start this by writing the reaction, or you can start it by determining what the conjugate base is and then filling in the reaction. I'm going to do it by writing the reaction out itself. So first things first, we need to remember what perchloric acid is. So perchlorate is going to be ClO4 minus, which means that our acid has to be HClO4. So if I do HClO4 aqueous plus H2O liquid, and I get H3O plus because I donate my H over here, I'm going to get ClO4 minus aqueous. So then it says to write the conjugate base. So the conjugate base is going to be ClO4 minus. So in this reaction, it's asking for the conjugate acid of the carbonate ion. Carbonate is CO3 2 minus, which means that if we want to get the conjugate acid, that means that this has to have been the base in our reaction. So if we react CO3 2 minus plus H2O, what we're going to end up with is H2O is actually going to donate its H to the CO3 2 minus to get HCO3 minus aqueous plus OH minus aqueous. What you'll notice is that an acid reaction has a product of H3O plus or H plus, while a base reaction releases our OH minus. So number 4 is similar to number 1. Which of the following represent conjugate acid-base pairs? Why or why not? Write the reaction if they are a conjugate acid-base pair. Supply the conjugate base or conjugate acid if they are not a pair. In order to start, I'm going to write this reacting with water. Doesn't really matter which one, but I'm going to have this H donate. We're going to get H3O plus OH minus. And what you'll see is that H2O plus H3O plus are a conjugate acid-base pair. OH minus and HNO3. In this example, we're actually going to start with the HNO3 plus H2O. We know that this is an acid. It's going to donate H3O plus NO3 minus. So this answer is no, because the conjugate base is actually NO3 minus. For C, I want you to do it on your own. I want you to see if you can come to the right answer. And then when you finish, unpause and check your work. All right, here we have a big idea. This is kind of our summary of what we just talked about before. So if you have a conjugate base for an acid, you need to remove an H plus. If you're trying to determine the conjugate acid for a base, you need to add an H plus. Right, because if you have your acid, you're going to lose an H plus and get your conjugate base. But if you are a base, that means you're gaining an H plus. And you're going to make an acid. One compound that's particularly interesting is water. It is an acid and a base. The word we use for this is amphoteric. All right, so water can act as an acid and a base. So here's an example of water acting as a base. If we have acetic acid reacting with water, acetic acid will behave as an acid and water will act as a base. So we'll donate the proton this way. We'll get H3O plus, and we'll get C2H3O2 minus. However, if we have a nitrite ion reacting with water, nitrite being a base will force H2O to act like an acid, and it will actually donate a proton to the nitrite ion. Last but not least, water can actually even react with itself, behaving as both an acid and a base. H3O plus aqueous plus OH minus. And so if we think back on the Arrhenius definitions of an acid and a base, we still produce the H plus ions and the OH minus ions that we had discussed earlier.